In the last set of videos, we talked about an aqueous solution. So now let's formally discuss what this means. All right, so we define a solution in chemistry as a homogeneous mixture of two or more substances. Now, the two or more substances, one of these substances is usually called a solute, and the other substance is called a solvent. So let's talk about what these mean. A solute, this is the substance that's present in a smaller amount. And a solvent, this is the substance that's present in the larger amount, in a greater amount. Okay. Now, usually, it doesn't have to be, but for this particular chapter, the solute will be a solid, the solvent will be a liquid. Now, it's not always 100%, always the solute is a solid and the solvent is a liquid. You can have a gas solute with a gas solvent. You could have a gas solute with a solid solvent. You could have a solid solute with a gas solvent. There's so many different ways that you could mix this up. But the idea here is that the solute dissolves in the solvent. We can also talk about a solution in terms of how well that solution conducts electricity. So the way that we define that is that if a species can conduct electricity, we call this an electrolyte. So an electrolyte is a substance when dissolved in water conducts electricity. A non-electrolyte is a substance that will not conduct electricity. Okay, now how do we test whether or not a solution is electrolytic or not? So what we do is and I'm going to draw a picture over here. What we do is make a kind of like a really, really primitive circuit. So what I'm going to do is make a little stand, and inside that stand, I'm going to put a light bulb. Okay, and then here's my filament. Yay, there's my light bulb. And now, attached to this light bulb, we've got two wires. And what I'm going to do is stick those two wires inside a beaker that's filled with a solution. So if I stick those two wires into that beaker, if the solution is electrolytic, that light bulb should light up. If it's not electrolytic, that light bulb doesn't light up. Now, sometimes you could have like the light bulb burn just barely. Like you can see the filament glow, but it's not lighting up like it normally should do. In that sense, we say that we've got a weak electrolyte, that it's not burning up the filament like normal. It's not it's not lighting up like a light bulb should, but you can see the wire glow. So let's try this out. Inside your textbook, there is a conductivity simulation. So let's see how this works. So this is pretty much the same setup as we did for that we did in our notes, but here inside our beaker, we've got different solutions. So inside this one solution, we're looking at sodium chloride. So the gray atoms here, these are the sodium ions. The green atoms, these are the chloride ions. So what we're going to do is drag our wires, drag the setup inside the beaker. Oh, look at that. All right, so as we drag the cathode and the anode, as we drag the wires inside the beaker, you're noticing that the light bulb lights up. Okay? All right, so I'll tell you what, let's drag it out. And this time, let's put in, let's try this next one, C12H22O11, which is sucrose. Okay, so this is sugar, basically table sugar. All right, so this time, if I drag the wires inside this solution, what happens? Okay, nothing's lighting up. Let me put the wires really in there. That's as far as they go. All right, so we know that sodium chloride is an electrolytic solution. Okay. Sucrose is a non-electrolytic solution. All right, well, what about this one? Let's jump over here to HC2H3O2. This is acetic acid or vinegar. So if I drag the wires here, it is lighting up, and it looks like you've got some movement. You've got some ions, but most of the molecules stay together as a molecule. Now, just to compare it, let's try the sodium chloride again. Let's see. Oh, so there is a difference here with the light. So you've got sodium chloride really burning bright, but then acetic acid doesn't burn as bright. All right. So with that being said, let's go back to our notes. Okay, so based on that demo, based on that interactive that we just did, we know that there is a strong electrolyte, we know that there's a weak electrolyte, and then we know that there's a non-electrolyte. So we know we have these three entities. What's the difference between the three? So let's talk about the strong electrolyte. So a strong electrolyte means that the solute completely dissociates. All right, so a strong electrolyte means that the solute completely dissociates. So what the heck does dissociate mean? All right, so let's use a chemistry term here, dissociation. So dissociation means the breaking up of a compound or a molecule into ions. And that could be a compound if you're dealing with an ionic compound. So ionic species. So let's say you got sodium chloride. Sodium chloride is going to break up into sodium ion and chloride ion. So none of the molecule is left. None of the compound is left. All you have are just the ions, the positively and negatively charged ions, and nothing else. Okay, so that's what a strong electrolyte means, that the solute completely breaks apart into ions. Okay, so for us, for that demo, that was sodium chloride. Sodium chloride completely breaks apart into ions. Now, a non-electrolyte means that the solute does not dissociate whatsoever. Okay, so for us, the non-electrolyte, that was sucrose. Okay. Now, what about the weak electrolytes? Weak electrolytes will break up, but it will be less than 50%. That means that it prefers to stay molecular. It prefers to stay intact as a molecule as preferred to be ions. So those are our three categories: an electrolyte, strong electrolyte, a weak electrolyte, and a non-electrolyte. Now, are there patterns to this? Absolutely. Strong electrolytes tend to be, if we look at the list of strong electrolytes, you got HCl, HBr, HI, HClO4, HNO3, H2SO4. All of these we can lump into one category. These are all strong acids. Okay. KBr, NaCl, these are all salts. Okay. NaOH, KOH, these are all strong bases. Plus other soluble ionic compounds. So, take-home message. A strong electrolyte means you're going to be dealing with either a strong acid, a strong base, or an ionic compound. Okay, so if you're dealing with an ionic compound, strong acid, strong base, automatically you've got a strong electrolyte. That means that solute is going to completely break apart into ions. If we go to the other side for the non-electrolytes, you got water, methyl alcohol, ethyl alcohol, sucrose, and most compounds of carbon, organic compounds. All right. So is there anything that we can lump together here? Non-electrolytes tend to be solvents. So non-electrolytes are usually the things that we're dissolving into. Okay, so that's why water, methyl alcohol, and ethyl alcohol, those are called out because usually those tend to be solvents for us. Okay, so not only are we dealing with solvents, but whereas over here on the left, we're dealing with ionic compounds, most non-electrolytes tend to be covalent compounds. All right. Now, more specifically, anytime you see carbon in the molecule, that's going to usually indicate that that's going to be preferred to be a non-electrolyte. Now, that being said, what about the weak electrolytes? What's going on? Okay, so whereas a strong electrolyte tends to be strong acids, strong bases, weak electrolytes will be weak acids and weak bases. And so that's why you're seeing acetic acid, hydrofluoric acid, and cyanic acid, because those are all weak acids. So weak electrolytes are going to be weak acids and weak bases. They will dissociate, but not as much as a strong acid will. Okay. And so that is our list of electrolytes. Out of the solvents available, water is really like the solvent of choice because we can use water to dissolve ionic compounds because it has a partial positive end where the hydrogens are and a partially negative end with the oxygen. So if this is what a water molecule looks like, where you have two hydrogens and an oxygen, and those dots that I just drew around the oxygen are electrons. If we look at that bond between the O and the H, the hydrogen end tends to have a partial positive end, and to indicate that there's a partial positive charge, I use a lowercase delta to indicate that. A delta plus tells us that we have a partial positive charge. And the oxygen will have a partial negative charge because it has it has the lone pairs. Okay, so because you have the partial positive and partial negative ends, water is a polar solvent. Because again, you have the partial positive and the partial negative charges. Okay. Now, a lot of times you may hear that we call water our universal solvent. Because water will work pretty much with a lot of stuff. It will work with a lot of different compounds. However, when we get to nonpolar compounds and nonpolar solvents or solutes, water doesn't work terribly well. But that being said, water works with a whole lot of stuff. So what happens when you take water, and you may have water as your solvent, but then you have, let's say, sodium chloride as your solute? How does sodium chloride actually make a solution? Okay, so what happens is that the crystal, and think of the sodium chloride crystal as like a square, a cube. Okay, so what happens is that this crystal starts breaking apart. This cube breaks apart, and we release the ions. So you're going to have a positively charged ion, and you're going to have a negatively charged ion, and that's the chloride ion. Now look at this picture. The sodium ion, the positively charged ion in the middle of this, look at what's going on with these water molecules. You have these water molecules, and they're arranging themselves so that the oxygen is closest to that positive charge. Okay. And so if you look at the other one, at the chloride ion, in this case, the hydrogens are closer to the chloride ion. So this whole process is called hydration. Hydration is defined as the process in which an ion is surrounded by water molecules arranged in a specific order. So let me write this down. The process in which an ion is surrounded by water molecules. Arranged in a specific order. Okay, and so you'll notice that when we're talking about the sodium ion and the chloride ions, the water molecules arrange themselves in a specific order. In this case, the oxygens are attracted to the chloride ion, to the sodium ion, because oxygen is partially negatively charged and the sodium ion is positively charged. Conversely, if we look at the chloride ion is negatively charged, and so the hydrogen ions, the hydrogens from the water molecules, have a partial positive charge. So they want to be positioned so that way they're closest to that chloride ion. And so that's pretty much, this is in a nutshell, the whole premise behind hydration. You take a solute, dissolve in water. This is what happens. The three-dimensional structure of that solid breaks up so that it releases these ions, and then the ions are bombarded by water molecules. Now, acids and bases make great electrolytes, and the strength of the acid will determine how strong an electrolyte is. So, like we said earlier, usually strong acids make great electrolytes because strong acids will want to give up or donate a hydrogen ion or a proton. Okay, so an example would be like HCl. If HCl breaks apart, it's going to release a hydrogen ion or a proton, depending on how you want to define it. Now, some acids, however, will not completely dissociate, like acetic acid. Acetic acid will break up and give you acetate ion plus a hydrogen ion, but we've got this double-headed arrow. And what this double-headed arrow indicates is that the reaction is in equilibrium. So that means that the reaction goes backwards and forwards. All right. Now we're going to talk a little bit more about acids and bases in a couple videos, actually 2 videos away. So we'll talk about acids and bases a little bit more, but we'll also, this idea of equilibrium, this is actually one of the biggest ideas in Gen Chem 2, and about almost the second half of the course of Gen Chem 2 is around this idea of a reaction that goes backwards and forwards. So this is something that we're gonna talk about in a lot more detail as we go forward in chemistry.